Alrighty, what is up everyone? Today we are recording a little tutorial video which is going to be split into three parts. First we're going to look at how to download Lidar data from the ELVIS platform. Then we're going to be looking at how to create contours and slope etc. in QGIS using that data. And then finally we're going to go into using LasTools with a bit of help from QGIS in terms of creating a understory vegetation density map. So let's get into the first part. So let's just imagine for a second we are looking here at Tasmania and we're looking for a waterfall. That's our context for this video. So we're looking around and we're thinking to ourselves, oh, you know, I actually quite like Mount Wellington. This is a cool place. What about this? Trestle Creek. I can't really see anything here, but I wonder if there's anything within this area that has a waterfall. Okay, we can see a bit of elevation in there. Maybe there's a little waterfall in there. I'm not too sure. Anyway, so we know where we're looking for. Let's jump onto ELVIS Lidar. So basically just type in ELVIS Lidar on Google, click on the first link that comes up, and you're taken here into the portal, which has all sorts of data from all across Australia. You can see New South Wales has some nice coverage, Queensland's got a bit, Tassie's got most of the state, because Tassie is really killing it in terms of the Lidar game. I don't know what the hell's Victoria's doing. Anyway, so now we're going to scroll down to the area that we care about. Now we know very well from looking around at our map exactly where Trestle Creek is and Trestle Mountain, which is this particular area here. So what we're going to do is we're going to try and select the area that we care about, which is this sort of like area of catchment here. Let's make the circle a little bit bigger than what we actually want, just to be safe, make sure we get all the data we need, and then we're going to close off the shape. So we care about this area. This is where we're going to get all our Lidar data from. So that includes point clouds, that includes digital elevation models. If you don't know what a point cloud is, point cloud looks a little something like this. They're even giving us some GIFs. Anyway, the point cloud looks something like this, where you've got a laser scanner that's created a whole bunch of dots, and that's what they've gone and done out in the bush, and your vegetation ends up getting rendered little something like this. Here's a great example of Lidar data. I mean, this is what we'll be looking at later on in terms of the data we'll be working with. We won't look at it in this 3D form because it's not really necessary, but the point is that this is the sort of data we'll be working with. Lots of dots. You can see the shape of the trees, you can see the shape of the ground too. So let's jump back into the ELVIS portal. Now you can see for the area that we care about, it has generated or discovered that we have a fair bit of data. So we have okay, so this is where you need to be really careful in what you're downloading. Is we've got data coming in from the Tasmanian government, which includes, as you can see from these little tiles here, we've got these are our 1 meter digital elevation models. So this is the shape of the ground. These will be images, TIFFs. And then we also have the point clouds, which is for the exact same tile. So if you see the very first tile here, which is 5095248, that should correspond to this one here. So it's the exact same spot, which is down in the bottom left of our area, except one is a digital elevation model, the ground model, whereas the other is the point cloud, which is going to include all the trees that we care about. So we could go and investigate the stuff from Geoscience Australia, because it looks like they have a bit, they only have a bit of data down in the bottom right hand corner of where we want. So we're going to ignore the data from Geoscience Australia because they don't have the data where we want. We're going to only look at the Tasmanian government data, which, as you can see, has tiles for the entire area that we care about. So we're going to select all the 1 meter digital elevation models, which is 59 meg, and we're also, while we're here, going to select all the point clouds, which is a total of 900 meg of data that we're downloading. So you can see that this data does stack up to be pretty hefty pretty quickly. So I mean, this is just a small area, just in this Trestle Creek area. You can imagine if you're doing like the entire Wellington range, it's going to stack up in gigabytes really quickly. So anyway, luckily it's quite a small area, so it's only 900 megabytes, and we're going to send this off. So what you do is extract the data sets to your email address and look for the email coming through to your email address, and you can then download the data. So we're going to wait for that to happen. While we're waiting for that to happen, we're going to jump into the folder, make a folder in your Windows Explorer where you're going to do all this stuff, and we're going to set up a folder some folders for ourselves to deal with this data. So what we're going to do, this is going to be the folder, the Trestle Falls revisit that we're going to work from. And so in here I'm going to create a folder called zip. I'm going to create a folder called las. I'm going to create a folder called tiff. And then we're going to create a folder called merged. So create these 4 folders here, and then we should be ready to extract the zip into this folder once it's downloaded. Alright, so we have our download now. It's going to take us through to a link and it's going to download for us. Fantastic. So now what we're going to do is we're going to wait for that to download. It's going to take a bit of time. Okay, so now the download has complete. This is our data, which is 869 meg after being zipped. So we're going to take that over to our Trestle Falls revisit folder. Now the reason we've created these 4 folders above here is because inside this zip there is folders, and inside this folders there's folders, and then there's zips, and there's zips in folders, there's folders in zips. It's crazy. So basically this, what I'm about to do, is a really easy way to extract all this data, get it all separated out and organized. So if you need to pause or slow down the video at any point from here, feel free to do so, but the first thing we're going to do right now is extract this data here using 7-zip. Now that we have this extracted, all the data in a non-zipped form, we're now going to search for zip within this root folder. We have 38 items here. We're going to select every single zip folder except for the original zip plus the zip folder. So now the zip, the folder that's named zip. So now we're going to cut all of these and put them into the zip folder. So now we're going to go back to the root directory and then go back into zip, so we make sure it extracts into the correct place. We're going to select all of the zip folders here. We're now going to extract them right here into this folder. So now we're going to go back into our root directory. We're going to search for LAS. Just keep in mind, sometimes you might come across LAZ files. That happens every now and then, but in this situation we're searching for LAS. And in fact we find nothing interesting, so maybe we are looking for LAZ files. There we go. So this is the situation where they're actually LAZ files. So we're going to take all the LAZ files that we searched for and come back into LAS. We're going to put the LAZ into the LAS folder. Now we're going to go back into the root folder. We're going to search for TIFF. We're going to grab all of the TIFF images that you can see here and nothing else, just the TIFF images. We're going to cut that and put those into the TIFF folder, and then we're going to go all the way back. So what we end up with here is the LAS folder with all the LAS files inside, and we have a TIFF folder with all of the TIFF files inside, and so that should be all ready and good to go for merging. So that's going to bring us on to the next step, I believe, which is jumping into QGIS. So when we go into QGIS, we're going to search up GRASS, QGIS with grass. If you install QGIS, grass should come with QGIS, and so we're going to open up QGIS in grass, because later on when we're doing the vegetation density analysis, we're going to need to use a tool that makes use of grass, that is part of the grass dataset. So anyway, we're here in QGIS. One of the first things I like to do is bring in my WMS layer. In my situation, I like to use the list map one. So the list map, in order to get the WMS connection into QGIS, you just need to right click on WMS, create a new connection, and in URL, you're going to put in the URL that you can see right here. I'm going to try and remember to put this in the description of the video, but this is the URL you want. And once you've put that in and created the WMS connection, you should have the list base layer, which you can then see here. Now we're going to zoom in on Tasmania. As you can see, it should look just like list map when you browse around on list map. Also, while we're at it, guys, please make sure that you save your projects as you're working on them, so that way you can come back to it at any point. So this one we're going to call Trestle Falls Revisit, and we're going to save this QGIS project so we don't lose our work and lose where we're up to. While we're here, we're also going to check our projection to make sure we're in the correct projection. We are not. So when just to make things look correct and not have any distortions, or to make sure you can refer to correct coordinates, because at the moment the coordinates are 1, 6, 3, 9. These are not eastings and northings. That's not what we use here in Tasmania. So what we're going to use is we're going to search for the projection. I've already got it here favorited, but it should be MGA Zone 55. So that's GDA 94 MGA Zone 55. That's what List Map Tasmania uses. So we're going to apply and OK that to make sure that our projection is set and we don't have any distortion. Cool. So we have our base map here. Now what we're going to do is bring in our elevation data. Now to do that, we're going to jump into raster, and normally you can just go into merge in order to merge all those TIFF images together that we were dealing with before, but I find that sometimes has errors. So my personal opinion is to use the virtual raster and then save out the virtual raster afterwards, because I find that just works most all the time. Anyway, so we're going to go back into the root directory that we created before. So as you can see, we have these folders that we made before, las merged in TIFF, and we're going to jump into the TIFF folder. So now we have all of the TIFF elevation images here. We're going to open those and hit OK on that. So you can see input layers, we have 18 TIFF images selected, the resolution average, that's fine. We're not going to put them into a separate band, that is AIDS, but we are going to allow a projection difference in case there is one. There probably won't be, but you never know. And so now we're going to save this virtual raster. We're going to go into our root folder, then we're going to go into merge, the merge folder we created, and we're going to call this Trestle Falls VRT, just to make it obvious that it is in fact a VRT file, which is a virtual raster. So then we're going to run, and we should see after we're done here, bang, here it is. So now we can see our elevation model of the Trestle Falls area. So you can see we've got this creek, the Trestle Creek, coming down here. You can see the slopes up to the mountain here. The white is obviously high, black is low. You've got the valley all the way down here. So this is our elevation model of the Trestle Creek area. Okay, now that we have our virtual raster, what we're going to do is going to save that out into a permanent TIFF format. So we're going to right click on VRT and then save as. We're going to make it raw data. We're going to go file name. We're going to save it into the folders which we were working in before. So if we go into Lidar analysis, our root folder here, we're going to go into the merged folder that we created before, and in merged we're going to save this as Trestle Falls DEM. We'll just call it DEM. We're going to save that. Now, my personal opinion, in order to save space, this is not really important for this, but for the purposes of just doing things correctly, when you're dealing with bigger images, we're going to jump into high compression, and for compress options, we're going to change it to LZW. You don't have to do this, but if you're working with a big image and you want to save space on your hard drive, it might be helpful to do this. By the way, we can see here that our resolution is horizontal 1, vertical 1. That means the size of the pixels in this elevation model that we are working with, if this comes up, just hit OK, no one really cares, is 1 meter. That's the resolution. So, in fact, if you zoom in on the elevation model, let's just zoom into Trestle Mountain itself. It's kind of hard to see because it's all a very similar color, but the point is the pixels are all 1 meter pixels, so that gives you an idea of what sort of detail you're working with when you're trying to find the waterfalls in this. So now that we have our TIFF rendered out, we're going to do our contour extraction, which is pretty easy. Open the processing toolbox, you just type in contour and then click on the first thing that comes up, that is contour. And then we're going to use our Trestle Falls DEM. We're going to set the contour interval to 2 meters. For situations where you're looking at more detail in the landscape, maybe you want to change this to a lower number, or maybe if you're doing more general topographic stuff, maybe you want to make this higher. It depends what you're doing, but for looking for waterfalls, my personal opinion is 2 meters is absolutely fine. So we're going to set the contour interval to 2 meters, and then we're going to save out the contours. I made this previously, but we're going to override it. We're going to call it Trestle Falls Contours 2. That's just a naming convention that works for me. Contours 2 meaning 2 meter contours. Just make sure you pick a naming convention that works for you, that is logical for you, so that way when you come back to these projects in the future, you understand what your files are. And to me, this makes sense, so just make sure you give it a name that makes sense to you. Yes, we're going to replace it, and we're going to run this again. So what the process is doing right now is looking at the shape of the land and producing the contours that we need. And so from these contours we can see in detail perhaps the shape of the creek. We'll be able to see if there's any rapids, any waterfalls in the creek. We'll see what we can see. Beautiful. So there we've produced our contours. If we want to, we can over here close off the DEM. So we're just looking at the contours with the base map in the background. And me personally, in order to get maximum visibility, I like to set the color of the contours to a bright magenta. That just makes it stand out the most for me. That's what I personally prefer. Select whatever the hell you want though. So now we're going to have a look at this creek. So we decided that this trestle creek is going to have a waterfall in it. Now, just quickly here, when I'm looking here at these lines, at these contours, I can, I guess, see the shape of the land. When I look at this right now, I can see, without this topographic base map, just looking at these contour lines, I can see a valley, I can see gullies sort of flowing in from the northwest into the main valley. I can see cliffs that have a southeasterly aspect. I can see a lot of landscape features just looking at these contours. Now, if you can't see this, if you can't see that just from looking at these lines, then I'm not too sure what to tell you other than have a look around on maps and try to relate the contours to shapes, try and sort of understand what the shape of valleys looks like. But if you're like me, you can see, okay, here we've got lines converging in of equal altitude. Clearly here we've got a depression, a linear depression. This is a water line. There's probably a water course at the bottom of this water line here. This must be a tiny creek. So now that we've figured that out, we can figure out that we've got a much larger creek coming all the way down this south-facing slope, and then down here we've got a larger river. But we were concerned, as we found before, we're concerned with this Trestle Falls area, which is Trestle Creek area, which is where we want to try and find our falls. So we're going to have a look up the creek, and we're going to see if we can find anything. So far we can see there's a little bit of a steep point there, but nothing overly dramatic. We're going to look a little bit further up the creek. Again, nothing overly dramatic. And then, hang on, what's this? Okay, let's zoom a little bit further here. We can see that the creek is sort of coming down, a little bit steep here, and it's coming down, a little bit of a drop, and then it's flat, and then it's flat, and then it drops. Let's have a look at this for a second. We've got a drop here of, these are 2 meter contour intervals. We've got a drop here of, let's say we start at this point, we've got a drop of 2, 4, 6, so 6 meters. So this creek has a drop of 6 meters over the course of, and I've just used the measuring tool up here to measure this, we've got a drop of 6 meters over the course of 3.5 meters. So let's just close that for a second. So if you're going down 6 meters and across 3.5, you can do some trigonometry for this. In fact, let's do some trigonometry right now. Okay, so who remembers their SOHCAHTOA from high school? We're going to do arctan of opposite over adjacent. So we would want the opposite to be the height of the waterfall, which is 6, and divided by the adjacent, which is the distance over which the waterfall falls, which was 3.5 meters in this situation, which gives us 1.0 rad. I'm going to convert this into degrees, gives us 60 degrees, basically. So what we can see effectively in our data here is that there's a waterfall that is at least 60 degrees in verticality. I say at least because what happens is LiDAR data will tend to smooth out topography, the shape of the land, a bit more than what it actually is in real life. So it's going to be at least a 60 degree waterfall. I know that for a fact because I've seen waterfalls that are in the data, like say 60, 70 degrees, but I visit them in person and they are very much vertical, if not overhanging. So we know that this waterfall is at least 60 degrees, so we know that it's not like a really boring, cascadey, flat waterfall. And like I said, it's 6 meters. Now, the other thing that you might want to check while you're here is the catchment of this waterfall, because it seems like we found a banger. It seems like we found something interesting. There's also something a little bit further below, but let's focus on this tallest part here. Let's see if we can calculate the catchment of this. Now, personally, I calculate my catchment. Ignore the fact that this is here. I personally like to calculate my catchment in ListMap because you don't need to be super accurate with calculating your catchment. You don't need LiDAR data to be able to calculate that. You just need a rough estimate. So what we're going to do is we're going to imagine that and again, maybe this takes a little bit of experience and understanding of the shape of the land in terms of how water flows across it. We need to draw a polygon around the area of land which would flow into Trestle Falls. Now it's a little bit awkward in this area where it's kind of flat. It's kind of like whereabouts is the water going to flow down. We can see there's a little creek here that definitely flows down into the creek, into the Trestle Creek there, this little tributary here. So we're going to try and select around that. We're going to jump up onto the ridge line of Collins Bonnet. We're going to follow Collins Bonnet until we get onto the ridge line that then goes between Collins Bonnet and Trestle Mountain. And then we're going to take this sort of ridge line down the south side of Trestle Mountain to approximately the place along here where the water would probably, where we reach the edge of where the water would sort of fall into the creek or not, because any rain that's falling here is going to flow in this direction out to the east, out to the west, out towards Hutchinson Falls. But any water that's falling, any rain that's falling here is going to flow down this slope into the creek and down here to this area that we're concerned about. And we can see that this polygon here has produced an area of 400 hectares. Now, in terms of a waterfall, this is a pretty moderate amount. It's helpful to, I guess, do comparisons with other waterfalls to understand what 400 hectares is, as to whether that's an important amount or not. Let's just do a quick comparison over here at Russell Falls. We're just going to do a really rough polygon. That Russell Falls is down here, by the way. Just going to do a really rough polygon around the catchment for Lake Nichols. It's hard to see where that flows out into, but we're going to assume that the catchment for Russell Falls is going to be approximately like this. That's 1,900 hectares. I know the size of Russell Falls in terms of the amount of water that goes down it, and so it's got effectively 1,900 hectares of water flowing into it. Keep in mind, though, that this is in an area of higher rainfall over here at Mount Field compared with over here on the Wellington Range, which is a little bit lower rainfall, so you have to keep that in mind when you're looking at your catchment. But anyway, we have the information that we need. We've found out without this little mappy thing that there is actually a waterfall here. We know it's 6 meters high, relatively steep, has a catchment of about 400 hectares, so as long as you go there and when there's recently been rain, there's going to be a decent amount of water flowing over it. Brilliant, we've just found our waterfall. Now we've got to figure out how to get down to it. So we can use our base map to sort of plot a course there. If we just zoom back and have a look, we can see that we have a track leading up to it. So I suppose you could go up the track here and walk across the contours. Maybe a little awkward. Walking across contours in the bush I find is generally more difficult than walking up or down. So personally, if I was to get to these falls, I would go up the track a little bit further and then get as close as you can. It looks like we're going to have to walk from this track down to the falls at a distance of 400 meters. 400 meters of bush bashing is what this is trying to tell us, which is an okay distance for a bash, I guess. So now what we want to have a look at, and this is something you can't see in this base map, is how steep is the land actually. Like, are we going to jump off any cliffs accidentally as we're visiting the falls? And certainly if you have a look here, there's some pretty cliffy shit going on here, or at least that's what it appears like. And we're going to do some analysis on that right now to have a look at how steep is this landscape actually. It's kind of hard to tell. So we're going to chuck in our Trestle Falls DEM elevation model, and we're going to output a slope. Again, here in the merged folder, we're going to call this Trestle Falls slope, and we're going to save it as a TIFF file. Save, run that, and bang, suddenly we have a slope map. We can see the slope of the landscape. Now, as we sort of saw before, looks like there's some cliffy shit going on here. If you're walking down this direction, you don't want to jump off this cliff. So let's try and put this in context to try and understand what slopes are actually going on here. Now, my personal preference for doing this, by the way, I just right-clicked and went into properties, and then you can go to symbology, is to create, I guess, bands of slope classes, so you can sort of compare the slope with actual values in degrees. So we're going to set the interpolation to discrete, I believe. How do we do this exactly? Equal interval. There we go. We're going to change the classes to 3. Classify. Why is this not working? Sorry, discrete. My apologies, I'm figuring this out as I'm going. We want discrete, equal interval, classes 3, but then we're going to manually change the values. So what I'm going to do is I'm going to set this value here to 55, and I'm going to set this value here to 45. So that way we know which land is above 45 degrees, which land is above 55 degrees, give us a good idea of which areas we should be avoiding. I'm going to apply that now. And then I'm going to change the areas that are less than 45 degrees to completely transparent so we can see behind them. Now we're starting to get somewhere. The reason I picked these values, 45, 50, is because it's like when you're out in the bush, once you get on slopes that are more than 45, 55 degrees, that's when the slope starts becoming a little bit dangerous, maybe. You might start sliding down, maybe fall off a cliff, I don't know. It depends on what the vegetation is like, obviously. Do you have much to hold on to? But we're going to roll with these values anyway. So for the values, the slope values that are between 45 and 55, we're going to give it an orange color, a nice orange color, and then we're going to change the transparency, the opacity, down to, say, 37%. Why not? And then for the values above 55, we're going to say this is dangerous. We're going to give it a bright red color, but again, we're going to change the transparency, so opacity is down at 55%, maybe. So the purpose of this is for us to see, okay, we're going to bash into this waterfall from this track. We're going to come down here. Are there any areas to avoid? We've given ourselves some slope values to put things in context, and we can see, okay, these areas here have a slope between 45 and 55 degrees. Could be a little bit dangerous, best if we can avoid them, but we can go down them if we need to. For areas that are red, which are above slope greater than 55 degrees, we should really be avoiding them. These are some serious cliffs we've got going on here. If we're going to be bashing in from the track, we don't want to fall off these cliffs, so let's try and aim a little bit further to the north, so that way we can get maybe tracking down here and sort of avoid the cliffy stuff. Again, this is just a theory. Obviously when you get in the bush, things might look a bit different than they do on the map. They always do. And so in theory, what we're going to do here is we're going to walk down this non-slopey area, we're going to reach the creek, and then we're going to walk up the creek. Sounds nice and easy, right? We're going to walk up the creek, and then we're going to reach the falls. Beautiful, brilliant. So that is a plan, that is a great plan that we have right here. We can see the track, we can see the falls, we can see the slope, and now we have a map that will help us get there. So let's save this out. Let's save this. We can use this to visit the waterfall we want to visit. So what we're going to do here in our QGIS project, we're going to go into project, and then we're going to go export map to PDF. I haven't yet figured out how to export to TIFF, not that it really matters. We're going to export this as a PDF. In terms of the resolution, have a play around with this. You might find, it depends on the situation, on what you want your DPI here to be. For this map, I'm going to guess we want about 200 DPI, but once you render it out, you will be able to have a look and see, okay, is this high enough resolution? Is it too pixelated and I need to up the resolution? Or am I showing too much detail and made myself a massive file and I need to downgrade the resolution? But for this, I'm going to take a guess and say that 250, let's play it safe. 250 DPI is what we want, which gives us pixel range of 4,000 by 3,000 approximately. That's the size of the image. We're going to create a geospatial PDF. What that means is you can chuck this directly into Avenza Maps or whatever the hell mapping app you're using, and you can use this to go out and actually navigate in the bush. So we're going to save this, and we're going to put it back into the folder we were working in before. So let's go into our Trestle Falls Revisit folder. We're going to save this as Trestle Falls contour and slope. Try to be descriptive, I guess. Contour and slope map. You can also say, if you want, GeoPDF to state that it is a PDF that is geo-referenced. You can use it out in the field. We're going to save that, and it's going to take a little bit of time to render out. It usually does. all done. Now we're going to jump back into our root folder here and have a look at this. So we've created a 3 megabyte file. That's a nice file size that is very manageable. And now we're going to have a look at what we've created. So this is a georeference PDF. If you were walking along this track, you'd be able to see yourself as a blue dot walking along here, and then you'd be able to decide, okay, I've reached about this point. This seems like a good point at which we should go into the bush, and then you sort of just dive down here, follow the contours, dodge the cliffs, get to the waterfall. Sounds easy, right? Until you encounter cutting grass and aids. Luckily in this situation there was no cutting grass, I don't think. Anyway, so that's done. That is the second part of the video done. We've created a GeoPDF showing us how to get to the falls. Okay, so the third part of the video, we're going to talk about something a little bit more advanced. We're going to need some more advanced software. We're going to be looking at how we determined the vegetation density. In a situation like this, we've got 400 meters of bush, which luckily in this situation is actually very open bush, very easy to walk through. But let's just pretend we're out in a super thick, scrubby area. And we want to figure out the best way of getting to the falls without encountering thick bush. We want to walk through the most open bush we can. So let's have a look at that. So what we're going to be working with is our LAS files that we got out before, or LAS files. We had 18 of them, and we're going to determine vegetation density using these files. Now what you're going to need for this is a free program called LasTools. You're going to download LasTools and it'll give you a folder basically, and in LasTools you've got bin. Bin is the folder that contains a ridiculous amount of different programs. Basically, this is all the same program, and these are just all different tools, but they set it out as if it's all multiple different programs. Anyway, the point is we just want to find the one that we care about. Now, the one that we're going to use first is going to be LasGroundNew. So in LasTools being LasGroundNew, that's where we're going to find this program here. Now, what LasGround does is it normalizes the LAS point cloud, and so I'll show you what that means. So let's just say you have a area, a slope, an area of bush, should I say, and it goes up like this, and you've got all sorts of vegetation up here. What's going to happen is the height value of this bit of ground here, hang on, let me restate this. The height of this bit of ground here is going to be higher than this piece of vegetation here. It's a very poor line, but please try to excuse my dodgy drawing. But the point is, what we're trying to say is that it's saying that the ground is taller than this part of the tree, according to a non-normalized last file. And that's not good for what we're trying to do, because if you're out in the bush and you're trying to measure undergrowth and you're trying to say that this vegetation is X meters above the ground, you want this, say, 5 meters up the tree. You want 5 meters up the tree to be equivalent to 5 meters up the next tree, because you want to say that the ground is essentially 0 meters. The ground is 0 meters. 0 meters down here, 0 meters down here, and this here is 5 meters, and this here is 5 meters. That's what you want. So what LasGround is going to do, let me make a new image here. What LasGround is going to do is it's going to normalize the Las point cloud so that the slope, the area that you're concerned with, is going to look a little something like this. This brown line is meant to be straight and flat, by the way. So what it means is that once it's all normalized, you can say that 5 meters up the tree is equivalent no matter where you are on the slope, keeping in mind that this spot here is up the hill, if that makes sense, and this part here is down the hill. So we've normalized the file. That's what we're trying to do with LasGround. So in LasGround, what we're going to do is find our Las files. This is a little bit complicated to work, this browsing system, but do your best to find your files within your computer. Here we go, Trestle Falls Revisit. We're going to go into the Las folder. Now we're going to use the wildcard to add in all the Las files. So it's either going to be .laz or .las, depending on what you downloaded. I'm going to use the wildcard .laz. I'm going to add all these files in, if it'll let me. There we go, yep. LAZ, now we can see all the tiles that we are familiar with. This is a familiar shape to what we saw in QGIS, where you can see, let's zoom out a little bit more, you can see the shape of these contours coming from the tiles, the Lidar tiles we downloaded before. If you jump into LasTools, you can see it's the same sort of shape, so you know we're onto a winner, we know what's going on here. Now, in the settings over on the right hand side, we're going to set it to wilderness in this context, because that's what we're dealing with in situations where you've got big buildings like a metropolis. You don't want the tool to count the top of a building as the ground, because the building is technically up off the ground. So that's what you'd use for a city setting, but in places like wilderness, we don't have situations like that. The closest thing you'd have to that is large boulders. So keep in mind that boulders may or may not get counted as part of the ground, depending on how wide and tall they are. But in this situation, we're going to pick wilderness, because that's going to be most appropriate for us. Leave it on default. If you've got the time, you can set it on fine, extra, ultra. I don't bother personally, not for this sort of stuff. Maybe if I was doing some researchy stuff, I would, but for the purposes of this, I'm not going to. Then we've got to compute heights and replace the Z, so that way we are properly normalizing our Las file. I'm going to output in LAS, because personally I like to have things zipped. My thought is that maybe it runs faster. I don't know if that's true, but we're going to set the output format to Las, and then we're going to run 64. Before we go, actually, what we're going to do is we're going to change this to run 4 jobs on 4 cores. Personally, I'm selecting that because I have a 4-core CPU. Let me just bring this over so you can see. I have 4 cores on my CPU, so I can make use of 4 cores for processing these files. For a tiny area like Trestle Falls, it really doesn't matter, but if you're doing a big area, this will definitely have an impact in terms of putting the job onto different cores. So I've got 4 cores. I'm going to run 1 file at a time on each of the 4 cores. I'm going to run it in 64-bit because it works, and then we're going to start that off. So now we can see on a little command prompt, it's slowly going to work through our files. Now, because I don't have a license for LasTools, I don't have the proper full version, it will put, I believe, a black stripe through some of the outputs, but we'll get to that later on. The point is that it's working a way to determine whereabouts the ground is, and once it's determined in the point cloud where the ground is, it can then put the heights of the branches and the trees relative to where the ground is. Okay, sorry guys for the confusion, but I've actually had some errors with LasGround new not working for me, so instead LasGround regular has worked for me. It's not something I've come across before, it just so happened to cause an error for me when making this video. Anyway, the point is, you can see it's trying to make these new normalized Las files, and there's 0 kilobytes, and it's not doing anything. What I did was I put all the original Las files into another folder called Las version 2, and as you can see, it's sort of working its way. It's created these Las files, and it's working away, it's actually doing something. So if we jump into regular LasGround, I did the exact same thing, but just in regular LasGround instead of LasGround new. It actually seems to be working, so that's nice. It's working its way through it. It should be done fairly soon, hopefully. The other reason I could tell that regular or LasGround new was not doing anything, but LasGround regular was, is because from my CPU graph I could see that regular LasGround was using a whole lot of my whole 100% of my CPU, whereas LasGround before was doing, LasGround new was doing absolutely nothing with it. So that's how we know that something was actually happening. You can see these files appearing here with the one extension on the end. We're going to grab these files and put them all into a separate folder for merging, because these are the ones we want to keep. You can see our CPU has finally dropped back down to very low, so that means that we're completely done. And as you can see, we've got all these files here. So now we're wanting to grab every second file from here, because these are the ones that are normalized, the last point clouds that are normalized. Easiest way to do that is to go into, I would say, large icons, and then we're going to resize this to be too wide. So you can see now we can select every second, and maybe there's an easier way of doing this. Now we can select every second file in this folder. Whoopsies. And once we've done that, we're then going to cut these files. We're going to go back into our root folder for the project, and we're going to call this LasNormalised. And we're going to paste them in here. So as you can see, these are all our LAS files with a little _1 extension on the end of them. So those are the normalized files. So now, instead of having them all in separate little tiles, what we're going to want to do is merge them all together. And luckily there is a tool for that. We have LAS merge, which is somewhere here within LasTools. LAS merge. We're going to run that one, and we're going to try and work our way back into the folder that we were in before. Trestle Falls revisit, LAS normalized, and we have all our files in here. We're going to add in the wildcard LAZ. That's going to chuck all our tiles into the program. It seems a little bit slow because of the larger file size of LAS versus LAZ, or maybe I just didn't click it properly. I apologize. Oh no, hang on, because the LAS and not LAZ. So we're going to add in the wildcard LAS. That's going to add in every single tile. And now we're going to output this as LAS. And we don't need to change anything because all this is doing is just merging the files together. We're going to click run, and it's super quick. For some reason, this tool, it's very, very quick. You just hit start, and then in a few seconds, it should just disappear to say, yep, I've merged all your files together. It's a little bit slower than usual this time. But once it's done, what it'll actually do is, instead of putting its file back into where you're working, where the original tiles were from, it'll actually put it into the LasTools bin folder, which is very confusing. But if you look in LasTools bin and you scroll down till you get to M, the letter M, where's M? Here it is, M. You got merge.las. Not very descriptive, so we're going to have to rename it, but we've got merge.las here. It's a 5 gigabyte file because we're working with quite a sizable area, though still pretty small compared with other areas that you might be working with. We're going to cut that, and we're going to drop it into the merged folder. And so we're going to call this Trestle Falls Point Cloud Norm, meaning normalized, merged. That makes sense to me, so I'm going to name it that, or 5 gigabytes. So now we get into the more technical stuff, and we're looking at vegetation density. Now we're going to jump back into Paint and try and understand why on earth we are doing what we're about to do. What we're about to do is look at densities of different vertical strata within the LAS point cloud. Now I'm going to draw our little, how do you do this? Paint. Going to draw our vegetation on our slope here on the ground. Now what we want to do is figure out what the undergrowth density is. Let me just color in our ground here. And what we're going to do in order to figure out the density is determine the amount of Lidar returns in the understory vertical strata relative to all of the returns beneath the top of that strata. So I'll draw you a picture of what I mean. So let's just say that our strata, we're going to use yellow for this, our vertical strata, we're going to say beneath the ground from beneath the ground to, and this is, if you look in the research papers that people have done on LiDAR point clouds, they'll find that generally an accepted value is going up to, let's see if we can type this in, 0.25 meters above the ground approximately. Some people use less, some people use more. It depends on the accuracy of your LiDAR data. But basically we have from beneath the ground up to 0.25 meters above the ground. That's going to be our first strata. We're going to call that the ground strata, I guess. So ground. And then the next strata is going to go up to where we decide the top of the understory is. Now that's completely subjective. Me personally, I like to say that it's 2 meters above the ground because I'm concerned with whether I'm going to be able to duck beneath the vegetation or not. That is, if there's any density vegetation above 2 meters, yeah, I don't really care about it. It's not going to affect me walking through the bush. The area that we do care about, I personally actually set this to a little bit lower than 2 meters, but for the sake of simplicity, we'll go with 2 meters. I'm going to set this to 2 meters. So we have our 2 strata here. We have our ground strata. We also have our we'll call it undergrowth. We'll call it our undergrowth strata. So what we're going to do is figure out here the ratio between the LiDAR returns in the undergrowth versus the ground. So let's give an example of that. Let's say we've got our LiDAR returns coming in from our plane well above, and we've got a LiDAR return here, another one coming in, LiDAR return here. This LiDAR return makes it all the way through to the ground. And we've got another one here, another one here, we've got our LiDAR returns here. So if we have a look at this situation here, we have an area where the LiDAR pulses have reflected from the vegetation on 4 out of 5 occasions. So in this situation, we have 80% of our returns being in the undergrowth area in this particular in the undergrowth strata in this particular area. Now let's have a look at an area over here where there's less undergrowth. Let's say you've got a LiDAR return or LiDAR pulse coming down, and you've got another few coming down here. Apologies for the poor drawing. We've got 4 out of 5 not hitting the vegetation. So in this particular situation, we have only 20% of our LiDAR returns in the undergrowth strata compared with the ground. So you can tell from the ratio, I guess the percentage of the undergrowth returns to the total amount of returns. In this case, 20% of the total amount of returns are in the undergrowth range, compared with over here, 80% of the undergrowth returns are in the undergrowth range, or the LiDAR returns are in the undergrowth range. You can tell the density of the vegetation. As you can see, the vegetation is a little bit thick. It's a bit thick here, but it's not so thick over here. So that's why we're wanting to separate our strata with LasTools. So now we're going to jump over into LasTools to make this happen in practice, and you'll see what I mean once I jump into the tool in terms of calculating the density in the different strata. So we're going to look for I believe it's LasGrid. It's been a bit of time since I've used this. LasGrid. So in LasGrid we're going to browse for our file, LiDAR analysis, merged. So this is our big point cloud. This is our big merged normalized point cloud. We're going to change the pixel size to 4 meters. I personally think that 4 meters is an appropriate. You can actually jump onto list map to see the density of your LiDAR data. So for example, this data that I'm working with is from the Tasmanian Flood Recovery 2019, has a pulse density of 4 pulses per meter squared, and so you can use this to sort of get an idea of how big your pixel size should be for measuring density. If you have a 4 meter by 4 meter area, 4 times 4 is 16. meters squared? Jesus Christ, man, it's been so long. 16 meters squared. So if we have 16 meters squared and 4 pulses per square meter, that's going to give us 64 pulses within our 4x4 area. So that's what we're going to roll with. We're going to say, okay, we've got 64 pulses. A lot of those pulses are going to get stuck in the canopy. They're not going to make it beneath the trees. We might end up with, I don't know, 20 pulses that make it down to the understory and the ground. We're going to have about 20 pulses to work with in order to determine our vegetation pixel. That seems like an okay amount. That at least was my logic when I decided on this 4 meter pixel value for density when dealing with 4 pulses per square meter LiDAR data. So we're going to jump back into our last grid. We're going to change this value here to point density 32-bit. Just to be safe, we're going to make it 32-bit. So this is where we're determining the density, that is the density of the LiDAR returns within the different strata. So we have our point density set on 32-bit. We're going to set the output format to TIFF. Now this is the part where we need to filter out the points into the strata that we care about. So we're going to drop in the normalised, remember that this is all normalised so that the ground is an elevation of 0 no matter where you are. We're going to drop any values where the Z is beneath, drop Z beneath, say, negative 0.5 meters. Now technically there shouldn't really be any values down at negative 0.5 meters, because that would imply that there's returns, LiDAR pulses being reflected from underground, which is technically not possible, but you never know when there's going to be, you know, distortions in your data set. So we're going to drop any values below negative 0.5 meters, and we're going to drop any Z values above, as we decided upon in our little diagram before here. We're going to drop any Z values above 0.25, that's the value that we decided on. We're going to drop any Z values above 0.25 meters. So that means that we're only getting, I just accidentally deleted that, we're only getting the LiDAR pulses that are either above negative 0.5 meters or below 0.25. So we're determining the density of the LiDAR returns in this lower ground vertical strata here. So we're going to get the density of the returns here along the ground. So that's what we're going to do in our last grid here. We're going to run this 64-bit. That's got an output, a TIFF for us. We're going to make sure that this is TIFF. We're going to run that and see what we produce. We're working with 5 gigabytes of data, so it's going to take a bit of time, but hopefully once we've done that, we should produce a pretty interesting density map. Okay, it's finished. Let's jump into, where did that save? Oh, here it is. Norm merged.tiff. So 1.5 megabyte file. Oh, here we go. Yep. Okay. Cool. This is it. Beautiful. So it's worked. So what we can see here is this is the density of the LiDAR returns in this ground vertical strata. Now, as you can see, it's very dense over in this area. It's not so dense along here, where maybe there's less pulses making it through the canopy of the trees. This is just the overall density. These black stripes here are because I don't have a fully licensed version of LasTools. You can, obviously that's a bit annoying. It looks kind of ugly, but if you get a proper licensed version, these black stripes won't appear here. So beautiful, that worked. Now we're going to rename it quickly so we don't get confused on what was going on here. So this was our Trestle Falls. We're going to call this ground strata return, because they're pulse returns, return density. That's what it is. It is the ground strata return density. Now we're going to do the exact same thing, except we're going to be measuring the undergrowth strata here. So if we jump back into our last grid, we're going to remove these parameters here, and this time we're going to drop Z below 0.25 meters. So we're dropping anything beneath this down in this strata here. We only care about this undergrowth strata here. We're going to drop the Z above 2 meters. Okay, so we're dropping the Z below 0.25 meters, dropping it above 2 meters, so we're only getting the undergrowth range here. That's the only places we're getting our pulses, our returns from in terms of measuring our density. So we're going to run the exact same thing with the exact same settings, run 64, we're going to start that. It's going to take its merry time to complete, and then we'll be able to start doing some comparisons with that CERN. Remember that these are absolute point density values, and so in areas where the LiDAR scanner happens to collect more pulses, it'll show that as being a higher point density. It doesn't mean that it's more thick vegetation there though, so that's why you need to normalize it, and we'll be normalize it again in terms of point density, and we'll be doing that later on in QGIS, so we'll get to that very soon. So I've just outputted another file. Let's have a look at this. It is 1.2 megabytes. This is our, and this is interesting because it looks a little bit different in its patterning. This is the density of the undergrowth vertical strata for these LiDAR returns, and as you can see, we've got all sorts of interesting patterns in here. We've got vegetation patterns and all sorts. I'm not too sure what's going on here, whether this could be the overlapping of the LiDAR scan lines or not. You can see there's a road coming along here, hence why it's less dense there. Anyway, it's very interesting, so we can see it work. So now we're going to rename this file that we've just created here. I'm just going to copy this and paste it in. And when this most recent file we've created, we're going to call it Trestle Falls Undergrowth Strata Return Density. And because that's what it is, that makes sense to me. So we now have our two TIFF files here which show the density of the ground strata and the undergrowth strata. Now we can put them relative to each other. So now we're going to jump back into QGIS. We're going to get rid of the slope and the contours just to remove a bit of mess, and we're going to drag in these TIFF files. I wonder if they have, there we go, beautiful. Okay, so now we can see what we were looking at before. Now these white things you can see in here, these are null values, and what this means is that in these areas here, because if I get rid of this base map, you can sort of see, you can sort of see the DM sort of show through when I toggle it on and off. So basically it's transparent, these white areas here. That's because there were no returns in that area, because either there was no vegetation or whatever else, the pulses never made it through the canopy. Interesting, we can see the flight lines in here now, so we can see the overlap between the flight lines. So the plane flew up here and then went across, and then it flew down here, so you can see the flight lines of the plane. And we'll have a look at our ground strata as well. It's interesting. So if we look just at our undergrowth strata, you can see that there's lots of missing data because there wasn't any undergrowth here. I'm assuming these are paddocks. Let's just verify this. I do have a Google satellite XYZ tile, which by the way is this URL here. If you want to add this in, we're going to drag this Google satellite in here, and as you can see from our undergrowth density, we can see that there is no colour in the areas of farmland, which makes sense because this is our undergrowth strata return density. There's no undergrowth density on the farmland. Makes sense, right? So we can tell that our data is telling us the truth. And then if we have a look at our ground strata, you can see we have data for everywhere except, look at these dams. There's no, on these dams here, the LiDAR pulse wasn't able to reflect from the water, so there was no information, no data that was able to be collected on these dams. Very interesting. Anyway, so now we're going to get into doing some calculations of the vegetation density. So to do this, we're going to jump into raster calculator, and this is what we're going to do. This is our special little formula here. We're going to go the undergrowth density divided by, in brackets, the undergrowth density plus the ground density. Now let's have a think about this formula. This is what's called a sort of a normalization formula. In this sort of situation, we're effectively doing what we did here with these percentage values. We're saying, okay, of the total amount of LiDAR returns we have here, which is the ground returns plus the vegetation returns, 20% of those returns were in the undergrowth strata. And so same sort of situation over here. Of these 5 returns, 80% of them were in this strata. So we're doing if you take 4, which is the amount of undergrowth returns, divided by the total amount of returns, which is 5, I mean, a simple bit of mathematics, 4 divided by 5, will tell you that you get 80% or 0.8. So it's this value that we're going to get out of our raster calculation here in that particular situation. Now, it does ask you to use a reference layer. So for our reference layer, we're going to use the Trestle Falls grounds, or whichever one of the return density files, just to give it something to work from as an example of what you want. And then in the output, we're going to go save to file, and in merged, we're going to call this Trestle Falls undergrowth density normalised. And so that means that we've effectively said this is what the density of the undergrowth is relative to the other returns beneath 2 meters in height. So we're going to run that, and this is it. This is our understory vegetation density map. So let's have a look at this. In this situation, black equals not dense and white equals very dense. And in fact, the transparent areas where you can see the trees showing through is very much not dense at all. So as you can see, the areas that are white, compare this with the vegetation, the areas that are white are very thick, very dense. You don't want to walk through those because it's very dense, full of vegetation, whereas the areas that are sort of either black or transparent are not very dense at all. Now, this is where we're going to bring in that processing toolbox, we're going to type in r.null. And this is the reason we wanted to start up QGIS with grass, because r.null is a grass tool. We're going to put in our density normalized. Now we're going to replace null values in this box here by 0. And what that's going to produce is Trestle Falls undergrowth density normalized, and we're just going to call it no null, because we're getting rid of these null values, these transparent areas where we have no undergrowth returns. And we're going to run that. Grass is a little bit inefficient, so it takes a bit of time. And now we have this, there's no holes. So now we can see the landscape. We can see we've still got our diagonal lines in there, kind of annoying, I know, but we could see in here the density of the understory across our landscape. Now here's where it gets interesting. We're going to grab our contours and we're going to pull the contours up and over the normalized vegetation density raster. We're then going to turn on the contours and bang. Now you can see. We're going to have a look for our waterfall a little bit further up. There's our waterfall. Now you can see we've got our waterfall. We've got our vegetation density. And we're also going to chuck in our slope. And bang, now we have a guide in order to take us to the waterfall we want to go. So if we're walking through the bush, we probably want to walk along these black areas, because black means not very dense, and we're going to avoid the white areas best as we can. We're going to try and walk down the slope and avoid these cliffs. We're going to walk down this slope, hopefully slot through here, and then get onto the creek. And so we're either going to have to walk up the creek here, or if it's flooded with water, that's not possible. We're going to have to walk along the edge of the creek in this white area. White meaning thick vegetation, so okay, maybe we need to walk through some thick vegetation to get up to the waterfall. And that's it. That's pretty much all we need to do in terms of doing calculations and determining stuff. This here is a good enough guide to get you to the waterfall. The only thing is that with this vegetation density in the way, you can't actually see where the track was. So we're going to bring that back here. There we go, there's that track, so you can see that as a dotted line there. Maybe you want to draw that in as a track. In order to do that, I'm not going to show you explicitly, but what you can do is just go to Layer, Create a Layer, make a shapefile layer, and then just manually draw in the track yourself, so you can layer that over the top of this vegetation density raster. But this vegetation density raster is pretty much all we need to get to where we need to be. So that's pretty much it. That is showing you how to create, using LasTools, the understory vegetation density, and of course before that we calculated contours and a slope. And as before, if we want to save this out, we want to take this out into the bush, out into the field. Pretty easy, just export the map as a PDF. Make sure you play around with the DPI as before to set it how you want. I'm going to set this to 250 DPI. And make sure it's a geospatial PDF, and we're going to save this out. And once we're and slope map and density. Once we save this out, we can then put it into Avenzo maps in the field, and we'll be able to know where the hell we are and how to dodge the thick bush. Like I said before, this particular situation, as you can see, there's a lot of black in here, so it really wasn't too much of a drama dodging the thick bush, but there are definitely situations before in the past where this has come in super handy. There's been super thick bush, but then little paths of not so thick bush where this has been really useful. Do keep in mind, though, that the currency of the LiDAR dataset will be a bit restrictive. What I mean by that is over here we've got areas of, say, plantation timber, which according to our vegetation density has no density at all, but maybe if the plantation gets felled and starts regrowing, it'll start becoming dense again. So you just have to keep in mind the currency of a data set and how that's going to affect things. This particular data set was captured in 2019, so really not a huge amount is probably going to have changed since it's 2019, but if you definitely get an older data set, like if we just scroll out here maybe further down to the south, you're definitely going to deal with data sets that are a little bit older. All this green is 2013, I believe, 2013, so it's older data. Shit's going to change since 2013, especially in areas that are like forestry areas where it's been harvested, the trees have been cut down or they're regrowing. It's going to become outdated. But in areas that aren't affected by forestry, you'll probably find that it's going to remain pretty accurate, the density of the vegetation shown in these maps. So yeah, like I said, that's pretty much it. Good luck with using this. If you do happen to use this, maybe using this for a uni project or some work, or maybe you're just doing this for fun because you want to find out where some waterfalls are, you want to do some vegetation density analysis and make some maps like this, yeah, leave a comment and let me know how you went, whether it worked, whether it didn't work, if you have any issues or if I didn't explain anything, because I'm sure in all my talking I didn't explain some things properly and I skipped through things very quickly and maybe you didn't understand as I went along. Like I said, just leave a comment and I can help you out as best as I can. But that's pretty much it for today. Good luck, guys, and I'll see you in the next one.